NEC Article 250.50 states that all grounding systems shall be connected together into ground at one or more locations to form a common ground system. NEC Article 250.52 states that the grounding electrode shall be interconnected with a grounding electrode conductor that meets the requirements of Article 250.64. Installing a separate ground electrode rod for a specific piece of equipment can create a potential difference between the existing electrical system ground and the new equipment ground. This difference can result in ground loops, which can compromise the safety of the equipment and personnel. In the event of a lightning strike, the potential difference between the existing ground and the new ground rod can cause current to flow through the equipment, increasing the risk of damage or injury. The impedance of the separate ground electrode rod can be higher than that of the existing ground system, which can reduce the effectiveness of the grounding system. Installing a new ground electrode rod outside the building's existing ground system can compromise the building's structural integrity. The use of a separate ground electrode rod may not be effective in providing lightning protection for the entire electrical system. Based on the NEC requirements, as well as the electrical safety concerns mentioned above, it is generally not recommended to install a dedicated ground electrode rod for specific equipment. The existing electrical system ground should be used as the primary grounding electrode, and all grounding systems should be interconnected to form a common ground system. A more detailed explanation of why not to install a separate grounding electrode is the potential for creating a difference in potential. Consider that the existing building ground is tied to the utility grid, which is itself grounded at multiple points. This creates a relatively stable and low impedance ground reference. Introducing a new, independent ground rod creates an entirely separate grounding reference point. The earth is not a perfect conductor, and its conductivity varies depending on soil composition, moisture content, and other factors. Consequently, during transient events like lightning strikes or even large load switching within the facility, a significant voltage difference can develop between the building's existing ground and the new, isolated ground rod. This voltage difference drives current through any equipment connected to both grounding systems, i.e., the original building ground and the customer's new ground rod. This current flow can damage sensitive electronic components, disrupt equipment operation, and even pose a safety hazard to personnel. Ground loops are another major concern. When multiple ground paths exist, current can circulate between them, creating what are known as ground loops. These circulating currents can introduce noise into sensitive electronic equipment, leading to erratic behavior, data corruption, and communication errors. In audio and video systems, ground loops often manifest as hum or buzzing sounds. In digital systems, they can cause data transmission errors or system crashes. The impedance of the grounding system is a critical factor in its effectiveness. A low impedance ground path is essential for quickly dissipating fault currents and protecting equipment and personnel from electrical shock. A separate ground rod, especially if it is not properly bonded to the existing grounding system, can have a higher impedance than the main grounding electrode system. This higher impedance reduces the effectiveness of the grounding system, making it less able to handle fault currents. The NEC mandates that all grounding electrodes be bonded together to form a common grounding system. This requirement is intended to minimize voltage differences between different parts of the grounding system and to ensure that fault currents have a lower impedance path to ground. The NEC provides specific requirements for the size and type of grounding electrode conductors used to interconnect grounding electrodes. These requirements are based on the size of the service entrance conductors and the type of grounding electrodes used. Installing a separate ground rod without properly bonding it to the existing grounding system violates the NEC and creates a potentially dangerous situation. The existing building grounding system is designed to provide a safe and effective ground path for the entire electrical system. It is sized and configured to handle fault currents and to protect against electrical shock. Tampering with the grounding system or adding new ground rods without proper engineering analysis can compromise its effectiveness and create a safety hazard. Lightning protection is another important consideration. While a single ground rod might seem like a good idea for protecting against lightning strikes, it is generally not sufficient to provide adequate protection for the entire electrical system. A comprehensive lightning protection system typically includes multiple ground rods, interconnected grounding conductors, and surge protection devices. The design and installation of a lightning protection system should be performed by a qualified professional. Installing a separate ground rod without proper coordination with the existing lightning protection system can actually increase the risk of damage from lightning strikes. Adding an isolated ground rod could create unintended consequences and potentially compromise the safety and reliability of the electrical system. It's better to ensure that the existing grounding system is properly installed, maintained, and inspected regularly. This includes verifying the integrity of the grounding electrode connections, checking the impedance of the grounding system, and testing the ground fault protection devices. If there are concerns about the adequacy of the existing grounding system, it is best to consult with a qualified electrical engineer or contractor to perform a thorough evaluation and recommend appropriate solutions. These solutions might include upgrading the grounding electrode system, adding supplemental grounding electrodes, or installing surge protection devices. However, any changes to the grounding system should be made in accordance with the NEC and other applicable standards. Now, to delve deeper into the technical reasons behind the recommendation against installing dedicated ground electrode rods, let's explore several key aspects. Firstly, consider the concept of equipotential bonding. The goal of a grounding system is not to attract lightning or to provide a direct path for lightning current to flow. Instead, it's to create an equipotential plane, meaning that all conductive surfaces within a given area are at approximately the same electrical potential. This minimizes the voltage differences that can cause current to flow through equipment or personnel during a fault or transient event. When a separate ground rod is installed, it disrupts this equipotential plane. Because the earth is not a perfect conductor, the voltage potential at the location of the new ground rod will likely be different from the voltage potential at the existing building ground. This difference in potential can create a driving force for current to flow between the two grounding points, leading to ground loops and other problems. Secondly, let's analyze the impedance characteristics of grounding systems. Impedance is the total opposition to current flow in an alternating current circuit, and it includes both resistance and reactance. A low impedance grounding system is essential for quickly dissipating fault currents and protecting equipment and personnel from electrical shock. The impedance of a grounding system depends on several factors, including the length and size of the grounding conductors, the type of grounding electrodes used, and the soil resistivity. A separate ground rod, especially if it is not properly bonded to the existing grounding system, can have a significantly higher impedance than the main grounding electrode system. This higher impedance can reduce the effectiveness of the grounding system, making it less able to handle fault currents. Thirdly, we should examine the role of the grounding electrode conductor. The grounding electrode conductor is the conductor that connects the grounding electrode such as a ground rod or ground plate to the equipment grounding system. The NEC specifies the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. The grounding electrode conductor must be sized to handle the maximum fault current that could flow through it. If a separate ground rod is installed, it is essential to ensure that the grounding electrode conductor connecting it to the equipment grounding system is properly sized and installed. An undersized or improperly installed grounding electrode conductor can create a high impedance path to ground, which can reduce the effectiveness of the grounding system. Fourthly, we need to address the potential for transient voltage surges. Transient voltage surges, such as those caused by lightning strikes or switching events, can inject large amounts of energy into the electrical system. These surges can damage sensitive electronic equipment if they are not properly suppressed. A well-designed grounding system can help to mitigate the effects of transient voltage surges by providing a low impedance path for the surge current to flow to ground. However, a separate ground rod, if not properly integrated into the overall grounding system, can actually exacerbate the problem by creating a reflection point for the surge current. Fifthly, it's important to consider the impact on sensitive electronic equipment. Modern electronic equipment, such as computers and networking devices, is highly sensitive to voltage fluctuations and noise. Ground loops and other grounding problems can introduce noise into the electrical system, which can disrupt the operation of this equipment. A properly designed grounding system is essential for providing a clean and stable ground reference for sensitive electronic equipment. Installing a separate ground rod can disrupt this ground reference and create problems for the equipment. Sixthly, let's discuss the regulatory compliance aspect. The NEC and other electrical codes provide detailed requirements for grounding and bonding. These requirements are intended to ensure the safety and reliability of electrical systems. Installing a separate ground rod without complying with these requirements can result in code violations and potential safety hazards. It is essential to consult with a qualified electrical engineer or contractor to ensure that any changes to the grounding system comply with all applicable codes and standards. Seventhly, consider the practicality of maintaining separate grounding systems. A single, interconnected grounding system is much easier to maintain and inspect than multiple, isolated grounding systems. With this single system, it is easier to verify the integrity of the grounding connections and to test the effectiveness of the grounding system. With multiple systems, it is more difficult to ensure that all grounding points are properly maintained and that they are all functioning effectively. Eighthly, we need to think about the potential for corrosion. Ground rods and grounding conductors are typically made of copper or other metals that can corrode over time, especially in certain soil conditions. Corrosion can increase the impedance of the grounding system, reducing its effectiveness. A properly designed grounding system should include measures to protect against corrosion, such as using corrosion-resistant materials and providing cathodic protection. Ninthly, the issue of unintended current flow can be significant. In a properly grounded system, current should only flow through the grounding conductors during a fault condition. However, in a system with multiple grounding points, current can flow through the grounding conductors even under normal operating conditions. This unintended current flow can create noise and interference, and it can also increase the risk of corrosion. Finally, we should look at the effects of magnetic fields. Current flowing through a conductor creates a magnetic field around the conductor. In a system with multiple grounding points, the magnetic fields created by the current flowing through the grounding conductors can interfere with sensitive electronic equipment. A properly designed grounding system should minimize the effects of magnetic fields by using shielded cables and by routing the grounding conductors in a way that minimizes the loop area. In summary, while the idea of adding a dedicated ground rod might seem like a simple solution for improving grounding, it can actually create more problems than it solves. A better approach is to ensure that the existing grounding system is properly designed, installed, and maintained, and that it complies with all applicable codes and standards. If there are concerns about the adequacy of the existing grounding system, it is best to consult with a qualified electrical engineer or contractor to perform a thorough evaluation and recommend appropriate solutions. These solutions might include upgrading the grounding electrode system, adding supplemental grounding electrodes, or installing surge protection devices. However, any changes to the grounding system should be made in accordance with the NEC and other applicable standards. The grounding system is a complex and critical part of the electrical system, and it should not be tampered with without proper knowledge and expertise.